Look at this thick, pressurized gas expanding inside a glass chamber. In the macroscopic world, gas behavior is an immediate reality. We can measure its pressure, watch it expand, and feel its temperature. To predict these behaviors, physics students are taught to rely on macroscopic equations, like the ideal gas law, PV equals mu RT. Robert Boyle was one of the first to quantify these effects in the 17th century, establishing that pressure and volume share a strict inverse relationship. But there is a gap in this macroscopic approach. Boyle's law describes what happens when you squeeze a container, but it provides no mechanical explanation for why the gas reacts that way. Relying solely on these formulas often leads to confusion when problems get complex. To achieve true mastery, we have to look past the visible cloud of gas and zoom in on the invisible mechanical reality. The kinetic theory of gases serves as the bridge between microscopic chaos and the physics we can actually measure. It starts with a specific rulebook. We assume a gas is made of a massive number of randomly moving point masses, and that the physical volume of the particles themselves is negligible compared to the empty space of the container. Next, we assume there are no intermolecular forces. These particles exert zero attraction on one another, except during the exact moment of a collision. Finally, every collision is perfectly elastic, meaning particles never lose kinetic energy to friction or internal heat. By defining these strict, idealized conditions, we create a mathematical environment to derive the macroscopic gas laws from the bottom up. This reveals the mechanical origin of pressure, the cumulative force of trillions of tiny elastic collisions hammering a wall every second. We calculate this using P equals 1/3 nmv squared, showing pressure relies entirely on number density, molecular mass, and mean square speed. To determine how fast these individual particles are moving, we use a specific metric, the root mean square speed, or VRMS. Looking at the numerator of the VRMS equation, we see that molecular speed is directly proportional to temperature. As a gas heats up, its particles accelerate. The denominator shows an inverse relationship with molecular mass. If you have a light gas and a heavy gas at the same temperature, the lighter molecules travel significantly faster. Pressure and speed are not independent variables. They are the direct mechanical results of manipulating the temperature and mass of the gas. In everyday life, we think of temperature as a subjective feeling of hot or cold. Kinetic theory provides a concrete definition. Temperature is strictly a measure of average kinetic energy. The equation E equals 3/2 kBT equates them directly. Crucially, this energy relationship stays the same regardless of what kind of gas you are measuring. Whether it's hydrogen or oxygen, the average kinetic energy depends only on the temperature. For an exam, this means temperature is a mechanical synonym for average kinetic energy. If the temperature is constant, the average energy is constant. If temperature is just motion, we have to consider how many ways a molecule can actually move. These are called degrees of freedom. A monatomic gas like helium moves strictly along the x, y, and z axes, having exactly 3 translational degrees of freedom. A diatomic gas like oxygen adds a dumbbell shape. It translates, but also rotates around 2 axes, totaling 5 degrees of freedom. The law of equipartition of energy states every degree of freedom gets an equal share of the total energy, exactly 1/2 kBT per molecule. This explains why different gases have different specific heats. A diatomic gas can hide extra energy in its rotations, meaning it takes more heat to raise its temperature compared to a monoatomic gas. This is why the specific heat at constant pressure, Cp, is always larger than the specific heat at constant volume, Cv. Despite these differences, Mayer's relation, Cp minus Cv equals R, proves that for all ideal gases, the difference between these two specific heats remains a universal constant. Zooming out to the environment of the entire container, we encounter one final metric, the mean free path. The mean free path, or lambda, is the average distance a molecule travels between 2 successive collisions. When gas pressure decreases, the molecules move further apart. This causes the mean free path to increase, as there are fewer obstacles in the molecule's way. However, it is important to remember that these rules are based on the assumption that particles are small and rarely interact. Real-world gases only act like ideal gases under 2 conditions: high temperature, where they move too fast to attract one another, and low pressure, where they are too sparse to interact frequently. Kinetic theory provides the mechanical foundation for the gas laws. By accounting for the microscopic choreography of mass and collision, the large-scale behavior of a gas follows a consistent mathematical logic.